So welcome back to lecture 3 on multivariable calculus. So I would like to start this lecture by correcting some definition which we have given in the previous classes. Recall I have told you the introduced somewhere in the big O or little o notation. So first I want to tell that, okay, so I want to correct this definition. Suppose f is a function from Rn to Rn, g is a function from Rn to Rk. We say that fx is equal to big O of gx as x tends to a. If limit x tends to a, norm of fx by norm of gx less than c. So this definition I want to really correct it. So it is instead of limit x tends to a, you have to write this. If the lim sup of x tends. So this condition, so I am changing this limit to lim sup. Okay. So what I'm saying that we say that fx is really big O of gx as x tends to a if lim sup of x tends to a, norm of fx by norm of g is less than c, where c is a positive constant. This condition 2 is equivalent to say that is equivalent to saying that there exists this is the symbol for there exists a neighborhood v of a, so that norm of fx by norm of gx is less than c for all x belongs to v minus. Okay, so condition 2 is equivalent to saying that there exists a neighborhood p of a, so the norm of fx less than by norm of gx is less than c for all x belongs to v minus. Now coming back, what you are doing. So let us start the lecture. So in the previous lecture, actually recall I have proved that two norms are equivalent. So I have told you that I have given the proof. I have told all of you that that to really. So the thing is, I have written basically the proof, but the thing is, I have told you that to really think about the idea of the proof, okay, so which I am going to explain now. So if you have not get that idea, so or if you have not tried, you have not given sufficient thought, you can stop, pause now, and you can really think about it. Okay, so let me give this proof then. So what was the theorem we have proved? Recall this. The theorem we have proved that on Rn, any two norms are equivalent. Okay? So this was the theorem I am interested in. Any two norms are equivalent. So we want to really prove this thing. Okay. Okay. So what is the idea of the proof? So recall we have defined something called homogeneous function. Okay. So what I'm saying that okay, so you have defined something called homogeneous function. So let us remove this thing. Okay, so I have defined homogeneous function. Okay, so recall that I have told you that. So suppose. So what is a homogeneous function? So let B be this be a normal in space. A function f from b minus 0 to really this r is called a homogeneous function. Of degree k if you have this relation f of rx is equal to really r to the power k fx. This happens for r greater than 0 and x belongs to b minus 0. Okay, so a function f from b minus 0 to r is called a homogeneous function of degree k if this is the thing. Now, because of this condition, okay, because of this condition say star, a homogeneous function is completely determined by its value on a unit sphere. So what is the thing? So if this S01, you take this thing. This is nothing but x belongs to b, so that norm x is equal to 1. This is the unit sphere with radius 1 and center at 0. Now suppose f is homogeneous of degree k. Then what happens? This if x is non-zero, then f of x is nothing but f of norm x by norm x, right? Then this is norm of s to the power k. Okay. Now suppose if f and g are homogeneous function of degree k, so that its value on the unit sphere are same. So this condition star will say that f will g. Okay, so let us call it double star. So corollary, if f is homogeneous of degree k, and g is homogeneous of degree k, so and assume that f of w is equal to g of w for every w belongs to this S01, then that will imply that f is equal to g, fx is equal to gx for every x belongs to b minus 0. So, okay. So what conclusion is the following? So you look at the functions on S01, homogeneous function of degree k. Okay, so conclusion is the following that conclusion is the following. If you look at functions on unit sphere on S01, so that is the one-to-one correspondence with homogeneous function of degree. So what is the correspondence? If you take this f here actually you can restrict just to S01. This is the thing. This is the map. Now conversely, if something is a function, say f tilde is a function on S01, I can define this f as new function fx by this thing. This by norm of x to the power k, f of x by norm x, f tilde of x by norm x. This x multiple 0. So one can, so the thing is homogeneous function of degree k and nothing but function on a0, comma 1. There is a one-to-one correspondence. Now coming back to what we wanted to show. So our theorem which we proved is the following. Any two norms on Rn are equivalent. Okay. Now the thing is, so suppose you take this thing. So what is the idea of the? I wanted to understand. So I wanted to talk about this idea of the proof. So what is the idea? Okay. So let this thing norm x a norm a and norm b be two norms on norms on Rn. So what is our goal? Our goal is to show that this thing norm is equivalent to norm b. So therefore, our goal is to show that there exists a constant c1 greater than 0 and c2 greater than 0, so that c1 norm xa less than equal to norm xb less than equal to c2 norm xa. This I have to show. So this is this and this you want to show for all x belongs to Rn. So this is equivalent to that there exists c1 greater than c2 greater than 0, so that c1 less than equal to norm xb norm xa less than c2 for all x belongs to Rn minus 0. If I can show that, then it is done. Now, so if this function norm xb by norm xa, we can show that this has an upper bound and lower bound, positive upper bound and positive lower bound, then we are done. Basically, this amounts to showing that this will imply that this norm A is equivalent to norm A. So this is the thing. So let Hx is equal to really norm xb and norm x. Okay. Okay. So to show that this thing is norm A is uh, so okay. So let Hx is equal to I define that norm xb and norm x belongs to b minus. To show that norm A is equivalent to norm B, so you should show that this function Hx has an upper bound and lower bound on b minus 0. Okay. Okay. So our goal is to show that. So there exists some c1 greater than 0 and c2 greater than 0, so that c1 is less than equal to norm. Okay. This is it. Now, so what is Hx? Oh, sorry. Sorry, this is there exists c1 greater than 0 and c2 0, so that c1 less than equal to hx less than c2 or x belongs to b minus 0. Okay. Now the thing is, this hx is a observed. So hx is a function on b minus 0, but it is much more than that. So you can think, you can pause for a moment and think. So what kind of function is Sx? So what I'm saying that it's observe that it's h is a homogeneous function of degree 0. So that means this will imply that h is a function of unit sphere, function on unit sphere. So you will say that, okay, so there are two norms here. norm A and norm B. So which norm? So in principle, there will be two unit sphere here. Okay. So, but the thing here it doesn't matter. This here it doesn't matter about the choice of unit sphere. In which norm you are taking the unit sphere. So what I'm saying, H is a homogeneous function of degree 0. So this means that H is a function on the unit sphere with respect to unit sphere. But here actually there are two norms. So the thing is, let us fix this norm A then. So let S01 is the unit sphere with respect to no norm A. X belongs to Rn, so that norm of X is equal to 1. Norm of X. So if I can show that, so if I can show that norm of XA is this, so this, so thus H is a function on S01. Since H is homogeneous function of degree degree 0, then therefore H is a function of on S01. Okay. Now the thing is, so if I can show that this H is bounded above by some constant C2 and C1, then I am done. Really, I will be able to conclude that norm A is equal to norm B. Now H is a function of unit sphere 1. So when can this is and H is a homogeneous function and positive. Okay, M is a, okay, it is a positive homogeneous function of degree 0. So therefore H is a positive function on 0, 1. Okay, so H is a strictly positive function on 0, 1. Okay, H01. Now the thing is, when can you say that H has one upper bound and lower bound? So if you will think a little bit, so then so if you think a little bit, so now the question. So what is the question? When H is a positive, when can H has a positive upper bound and lower bound on this 01. So, okay. So if I can show that somehow, you can show that H has a positive and upper bound and lower bound and H01, then I am able to, I am done, right? So this will happen in two cases. So the answer is yes. The answer to above question is yes. Question is yes in two cases. Two natural cases in two cases. So first in the following case, okay, not in the following case. First, if you somehow, if this S01 is compact, if S01 is compact. Second thing, okay, this H is a continuous function on S0. So if h is a continuous function on S1, okay. Now what is hx? Hx is really this norm xp by norm xa. So this function, so observation, so x going to norm xa is always continuous. So this, so h is continuous on S01 if and only if and only if this x going to norm xp is continuous on S01 and the topology of S01 is coming from the norm A. Okay, so call it thus if thus we want so the thing is if I can show that some S01 in some norm A, S01 is compact and this S is continuous function on S01, I am done. But H is continuous function on S01 is amounts to showing that X going to norm X is continuous on S01 norm A. So the thing is if norm A is such that this S01 is compact and second thing X going to norm XP is continuous on S01, then we get norm A is equivalent to norm B. If I can find a norm A so that this S01 is compact and this X going norm XB is continuous on S01, then we will get this thing. Now, okay, so another thing. So third thing, actually, this thing, if I can show that X going to norm XP, so the second thing is it's so let's consider this third statement. If suppose this XP norm XP is continuous on this whole space V into norm A. So if this is the thing, if you can show this 3, then 3 will imply 2. So, so if we can, so we can find a norm A, say, so that this thing happens. This A01 is compact. And second thing is X going to norm XA is continuous on this, on V norm top, on V top, sorry, on Rn. Okay. So here not B, Rn. On Rn and topology of Rn will conduce. Then we am done. So what we will get that if we can find a norm as that H01 contact and this if we can show that X going norm X is continuous on Rn and topology is coming from norm A, then I am done. Okay. Then I am then this will imply that norm A is equivalent to norm A. Now, if you think about for a moment, what is an example of norm where this S01 is compact? So you will see that you will say within a minute. So just pause for a second and think about this question. The question is give an example of norm where this S01 is compact. You will say that if this norm A is little L2 norm on Rn, If norm A is equal to, then certainly this. Then this S01 is compact. You know that. So what is little L to norm? You know that's little norm of x is equal to x1 square plus x2 square plus xn square square root. So if you look at this proof, actually I have chosen this first. I have taken in the first step. I have taken this little L to norm, and and then I have showed that any norm is continuous on this Rn with respect to the little norm. Now, second thing, then I have brought unit sphere into the picture, and then I have carried the proof. So what I'm saying, if you look at our proof, I have chosen this first little L to norm, and little L to norm, this norm is little L to norm, and I proved the second thing first. Then I have brought this unit sphere into the picture to conclude that norm, any norm is equivalent to norm 2. And then using transitivity of equivalence, then I have proved that. Okay. So this is the idea of the thing. Okay. So I have proved this thing. Okay. So this is the idea for the proof. So let us proceed to, let us come back what you were discussing in the previous class. Okay, so the thing is, okay, in the previous lecture, actually, what I have proved some proposition like this. Okay. So if let A belongs to GL and R, which does the norm of I minus A is less than 1, then M is equal to summation M is equal to 0 to infinity I to the power I minus A to the power M is convergent and A is invertible, and with A inverse is given by M is equal to M is equal to 0 to infinity I minus A to the power M. Okay, so this proposition I have proved. Now I have to prove another proposition today. Now onwards pay some attention. So proposition. Let B belongs to GL and R. Okay, so let B belongs to, sorry, let A belongs to GL and R. Let B belongs to M and R. This is that norm of B minus A is less than A inverse, norm of A inverse. Then B belongs to GL and R. Okay, so this A implies that GL and R is an open set in M and R. Okay, so B is second. B says that A going to A inverse is continuous on GL and R. So proof. So you will prove the you will use the proposition, previous proposition which I proved in page 32. Okay, so the thing is page 32 is the special case of A where A is identity. So if A is identity, then this right hand side is 1. It says that if I minus A is less than 1, then A is invertible. Okay. Now I have to prove A by using this previous proposition. So okay, so I have some information about B minus A, and I want to bring somewhere identity. So I write B minus A something like this. If I will take common A, because A is invertible, I can take common. So A into A inverse B minus identity. Okay. Now what is A inverse B minus identity? A inverse B minus identity is same thing as A inverse into B minus A. I take the norm in both sides. So this will be less than equal to A inverse norm into B minus A norm. Okay. Now this B minus A norm and A norm of A inverse, this is strictly less than 1. This is less than 1 by hypothesis. This is less than 1 from hypothesis. So that so this will imply that so from proposition page 32. So this which I have proved this thing. So this proposition, what is that? Yeah. So this is the proposition. If norm of I minus A is 1, then A is invertible. So from proposition in page 32, we get this thing. A inverse B belongs to GLNR. So if, see, the thing is A inverse is a invertible matter. Since so that's this will since A inverse is invertible, so this will imply that B belongs to GLNR. This is clear. Now second thing is I want to prove that B A going to A inverse is continuous. Okay, so we have to prove the continuity at A. So the thing is, what is the meaning of continuity? Meaning of continuity is the thing. If you look at f(x), suppose f is a function from x to y, and x and y are metric spaces. The meaning of continuity is if x goes to A, then this will imply that fx is going to f. So f is continuous at A. This what does that mean? That means if x converges to A, then fx converges to f of A. That means if x is sufficiently close to A, then fx is sufficiently close to f of A. Okay. So that so roughly saying that you can control the difference, control the distance between fx and fa by x minus a. By this distance between x and a. So roughly speaking, that you can control the distance between x and fa by distance between x and a. Now, what is the idea of this? It is the idea the one variable thing. So let us understand what is the one variable case. So in the if n is equal to 1, this say that x going to x inverse is continuous on r minus 0. How do you prove that? So an idea if case idea for this n is equal to 1, or this n is equal to 1, how do you do this? This is so this proves this is the fact. So you have to prove that if r minus r2 are given by this thing, fx is equal to really 1 by x. This is the map. So what was our claim? Claim is that f is continuous at. So this is x not equal to 0. The claim is f is continuous at a. Okay, and this a is non-zero. So how do you do that? So you do that like you write this fx minus f of a. Okay. Now this is nothing but 1 by x minus 1 by a. This is nothing but a minus x by xa. Okay. So this is my picture. This is my picture. This is my 0. Suppose this is my a. Okay. Okay. Now what is fx minus f of a mod? This is nothing but if you look at mod of a minus x, 1 by mod x by a. Now observe that if x goes to a, this if x goes to a, this if x goes to a, this a minus x goes to 0. Okay, and this a is a fixed number, non-zero number, so this whole thing will go to 0. Okay, so what I'm saying, if x goes to j, this whole thing will go to 0. So only problematic thing is this thing, 1 by mod x. Okay? So if this 1 by mod x is bounded, then we are done. Then that will show that f is continuous at a. Okay, but this is a very highly unlikely situation on r minus 0. So 1 minus mod x cannot be bounded. So one thing you should know that this continuity is a local property. Okay, so what does that mean? That means if you want to study continuity of a function at a, it is sufficient to look at the behavior of the function in a neighborhood of a. So the thing is, okay, so now I will take a neighborhood. So in your real analysis course, you take this neighborhood W. W is really x belongs to say r minus 0, so that mod of x minus a is less than a mod of a by 2. You take this neighborhood. So in place of mod a by 2, you can take, so this is the mod a by 2 neighborhood. In case of mod a by 2, you can take any delta where delta is less than mod a. From geometry, it is clear. Okay, if delta is less than mod a, then mod x will be greater than something, some positive number, and that will imply that if mod of x minus a less than delta, where delta is less than mod a, then that will imply that this this double, if x belongs to this neighborhood, say, that will imply that mod x will be greater than some positive number. That will imply that 1 by mod x is bounded. So, but the thing is, in your analysis course, people usually take this mod of a by 2. Okay, so if x belongs to W, then from triangle inequality, we'll get mod x is really a minus x minus a, or a minus okay, x minus a okay, a minus x, and this is greater than equal to mod a minus mod x, and this, since mod of x minus a is less than a by 2, so this is really less than mod a by 2. Okay. So that will imply that 1 by mod x is less than 2 by 1. So okay, so you call this as star, okay, and call this as double star. So from star and double star, we get this thing, fx minus f of a. So this is okay. You get this is less than 2 by this 1 by mod x is less than 2 by a. So if I will put that thing, this will be less than 2 by mod a square into mod of x minus a, and this value is for this x belongs to W. So call this say I. Okay, so okay. So from I, this is clear that from I it is clear that if this line, so that if x goes to a, this will imply that f of x will converge to. So if x goes to a, that means x will eventually lie in W. So you can really, this I will be valid. From I, it is clear that if x goes to a, then fx goes to this will go to 0, then fx will go to f of a. Okay, so this shows that if it's this fx is equal to 1 by x is continuous on one dimensional case. Okay, so for the natural for this thing, for any n, okay, for n greater than 1, so we want to really so we want to use exactly the same idea. Okay, so the thing is for n greater than 1, one problem is this is GLNR is not commutative. So a dot b may not be equal to b dot 2. So for any n, so this, okay, so let us see. So this is the idea. So let us see. Okay, so this, let us call this as idea of B for n is equal to a proof of B for okay. So let us prove this thing B. So proof of B is the following. So okay, so we want to prove the continuity at A. So let A belongs to GLNR be fixed. So what is our goal? Goal is the following. Okay, goal. If B is equal to A, B converges to A, claim. Let us write its claim. Our claim is if B converges to A, this will imply that B inverse will converge to A. So like the one-dimensional case, we have estimated this fx minus f of A, and we have get what this is get. We have written down fx minus f of A in form of this A minus x. So this will be x inverse A minus x inverse. So we will write this. Okay. So B inverse minus A inverse in this form. So if so, this B inverse minus A inverse, you will take common. So B inverse. So this is I minus B A inverse. Okay. So this will be B inverse. This is A minus B into A inverse. So this will imply that if I really B inverse minus A inverse, so this is equal to B inverse A minus B inverse. So this will be less than equal to norm of B inverse, norm of A minus B into norm of A inverse. Okay. So what I am getting this B inverse minus A inverse less than equal to B inverse norm, A minus B norm, inverse norm. Now if I am calling this IISc, so if A goes to B, if A converges to B, this thing norm of A minus B will go to 0. So this will go to 0. So and this A inverse is norm of A inverse is a fixed quantity because A we have fixed. So whole thing is really go to 0. Likewise, like the previous case, this is the only problematic thing. Okay. Now if we can bound this norm of B inverse, then we are done. So and it is not possible to bound norm of B inverse in whole GNR. So, but I told you that continuity is a local property. If we can bound this thing, norm of B inverse in a neighborhood of A, then we are done. And we were going to we will see that this norm of B inverse is bounded in a neighborhood of A. So if you can bound norm of B inverse in a neighborhood of A, then we are done. So what is the neighborhood? So in the previous case, what we have taken, this is the neighborhood. X belongs to R minus 0 by mod of X minus A is less than mod A by 2. In this case, if you think about little bit of A, if norm of B inverse, B minus A is less than norm of A inverse, then B is invertible. So definitely I have to choose a smaller neighborhood, smaller radius than this norm of A inverse. So what I want to take that let W be is equal to, so let W is equal to B belongs to G ln R, so that this thing norm of A minus B is less than this thing A inverse by 2. Okay, so this is same thing as B belongs to okay, so B belongs to G ln R. So this is norm of A inverse B into norm of A inverse is equal to less than half. So clearly by definition, from this definition, this W is an open neighborhood of A. Clearly, W is an open neighborhood of A. So if B belongs to W, that means this quantity A inverse B into norm of A minus B into norm of A inverse, this is bounded. So if W belongs to B, if B belongs to W, from I it follows that you get that this thing B inverse minus A inverse norm is less than norm of B inverse by 2. So now I play with the triangle inequality. So this is even norm of B inverse minus norm of A inverse is less than equal to B inverse minus plus norm less than B inverse by 2. So that will give you that B inverse by 2 is less than A inverse, norm of A inverse. So that will be, okay, so this will imply that B inverse is less than 2 norm of A inverse. I am calling this 2. So this from A, and so I have in 2 say that I have a bound in the norm of B inverse in the neighborhood of A. Okay. So from 1 and 2, it shows that since this norm of B inverse is less than 2 into norm of A inverse, from this 1 and 2, so if B belongs to W, for B belongs to W, from this, let us for B belongs to W, from 1 and 2, from I and 2I, we get this thing norm of B inverse minus A inverse is less than 2 A inverse square into norm of A minus B. Now let's call this 3. From 3, it is clear that so if B goes to A, that will imply that B inverse goes to A inverse. Okay. So this proves the proof of this proposition, which I have proved. That A going to A inverse is gone. So thus A going to A inverse is continuous. So this B inverse will so thus this map X going to X inverse is continuous. Okay, so we have proved this thing. Okay, so we have proved this thing, and this thing is right. This thing. So let us write here. Okay, so let us prove a new thing. So recall that. Okay, so let us start a new topic. So now onwards, please pay little attention. So recall that in the first lecture, I told you that we want in this course, so actually we want to really okay, so one thing I just wanted to tell you always, so before starting this lecture, I can tell you that I just want to inform that in my web page, we will find some assignments. Okay, so which I usually give the students here. So you can try those assignments and you can solve this question. So for instance, I can show you in my web page. So you can just type, this is Naik, and you can go to my home page, and you can go to teaching. So you can go to multivariable calculus, and you can go to for this. This is my assignment. You can click on that, and so these are my questions. So this. Okay, so you can solve these exercises so that you will get a good understanding on the subject. Okay, so okay, so okay. So hopefully on some lectures I will discuss about it. Okay, so now the thing is the okay. So now let us coming back to the what we are discussing. So recall that I in the first class itself I told you that our goal is to really so to define the notion of differentiability on Rn. Okay, okay. No, sorry. So in the past lecture, I told you that our goal is to develop calculus on Rn. So and our prototypical model is R. Now the thing is on R what on the single variable calculus you have studied the differentiability and differentiation and integration. So today we want to really extend the notion of differentiation on from this single variable calculus to multivariable calculus. Okay, so let us discuss that. So this is a discussion. So let f is a function from R to R. Okay. So okay, so we say that so this f is differentiable at a. So diff is the acronym for differentiation, differentiable. Diff stands for differentiable. Seeable. Okay. Whenever so we say that f is differentiable at a, if this thing happens, if limit s tends to 0, f of a plus h minus f of a by h, this limit exists. Okay. If this exists, then we will say that um, this thing f is differential, right? And we define in this case f prime a is nothing by this limit s tends to 0, a plus h minus f of a by h. So we want to define this thing. Okay. Now this is the notion of differentiability for function from R to R. Now we want to define this notion for a function from Rn to Rm. Suppose, so now consider, so so in this case, let us assume that Rn f is a function from Rn to Rm. Okay. If f is a function from Rn to Rm, observe that this definition will not extend for functions from Rn to Rm. So what I'm saying that if, say, suppose f is a function from Rn to Rm, we want to say that f is differentiable. Suppose a belongs to Rn. So, and using this definition, which we have seen from R to R, so we want to give a notion of differentiability for this function for this function f, which is different from Rn to Rm. So observe that this definition will not really generalize. Why? Because if you look at this star, okay, this star doesn't make sense for n greater than 1. This star doesn't make sense for general for functions from Rn to Rm. Why? Because if f is so observe, star doesn't make sense for n greater than 1, because for higher dimensions there is no notion of division is there. So you cannot divide a vector by vector in higher dimension. You can divide a vector. So this definition doesn't make sense. So there are some natural obstruction. So we cannot thus, okay, so we cannot extend the notion of differentiation so from R to Rn. Okay, so we cannot. So what we have to do? We have to define the notion of differentiation in different way. So upon in mathematics, what happens? Okay, in mathematics, actually, what happens? Suppose there is some concept, okay, or some notion or definition is there in some class, or in a simple on a setup, or on a, so there is a notion or concept defined in some class. So, but the thing is, we wanted to extend that concept in a much more bigger class. But the thing is, it may happen that the concept which was earlier there, that may not easily extend to a bigger class. So what you have to do, you have to really modify that definition in the smaller class in a such a way, okay? So that will be equivalent to the definition in the smaller class, okay? And that can be easily extended to the extended to a bigger class. So what I am saying that in mathematics, it may happen that there is some concept or notion which is suitable in a smaller class is there. So we want to extend that definition to a bigger class, but that may not extend the thing, the two bigger class. So what happened? That you have to modify that definition in the smaller setup or smaller car in a such a way that will fit that will easily extend to a bigger class, and that will also that is also same, that will be also same with the smaller cars. For consider this example, uh, if you know that in the is happening